Hi everyone. Today, let's talk about using AI for material science applications. So, in this video series, I will focus on various scenarios and detailed applications within material science. Once we have covered this AI for material science part thoroughly, we will move on to explore other exciting areas where AI is making an impact, such as healthcare, climate science modeling, and so on. Interestingly, many of the approaches developed for AI in material science can also be applied as it is. We need to make few changes, of course, but broadly, a 90 percentage or the 90 to 95 percentage stage of the things can be applied to healthcare and other fields, which creates a broader scope for innovation. So, what you see here are so many amazing AI models for images, text, and video generation. We can see that the results generated are pretty stunning. These models can create beautiful art, generate hyper realistic videos, and even write essays. They are impressive, there is no doubt about it. But let me ask you this question. Is it advancements in video and image generation that we as human beings truly need to focus on, or should we direct our efforts toward developments, advancements in science, like developing materials that can revolutionize industries and solve real world problems? So this is my question, to you. And to me, the answer is clear. It has to be science, and in particular, material science. You know, But the fact of the day is that AI has already shown its potential in science. There's a lot more to go, there's no question about that. But we are already seeing a lot of applications of AI in drug discovery, climate modeling, and even astrophysics. And now AI is starting to make its impact in material science as well. So right now, as I'm speaking, we can use AI to discover new materials faster. We can predict properties with higher accuracy. We can optimize complex processes that have traditionally taken years of trial and error. So AI can presently transform how we innovate in materials. Whether it's creating lighter alloys for aerospace applications, stronger polymers for construction, or more efficient semiconductors for electronic industry. So the possibilities are endless with AI. The biggest question, there are a lot of questions, but the biggest question that lingers for me today is whether AI can truly achieve what we hope it can. But during my PhD, one of the toughest questions I faced was this, while everybody agreed that the AI models I was developing worked very well for the materials I was studying, how could I be sure that they were really working? Were they interpretable? Could I truly understand what the model was doing? Questions like this were a constant challenge for me. So that's why my work has always focused on trying to unbox the black box of machine learning. However, even today, no one has been, not just me, not any researcher in the world has been able to fully explain, quote unquote, fully explain why AI models work so well in so many material science applications. That's the truth. Nobody has been able to fully uncover the black box in the of the machine learning, and it is disheartening at times, because but it's also motivating that there is something for us to work on. Correct. uh, Yet what keeps me motivated, is a fundamental belief. I think it's possible to model the entire universe using a massive machine learning model with an enormous number of parameters. So this faith or belief stems from the universal approximation theorem, which was discovered in 1990s, and in that's something it's quite remarkable theorem, and The incredible success of machine learning in other domains like natural language processing, which is already a very complex function space to learn image generation, video synthesis. If the machine learning models can truly work in those applications, it should be able to model complex physics in material science as well, and that really comes from the universal approximation theorem. um, I personally believe if we have enough data, we could achieve something extraordinary using AI for material science. The physics based equations we use today are very simple and elegant, right? They are very elegant, but I personally believe they may not be enough. They're undoubtedly very effective, but they often rely on assumptions, that personally I feel very limiting. I find it very limiting. For example, I will tell you an example about this. Even basic concepts like interactome potential, that's used in molecular dynamics, and other simulations, which I will talk about in the upcoming lectures. They're often based on empirical evidence, and they are not fully exact. So, in my view, um, machine learning has the potential to completely replace many physics based approaches, offering a more comprehensive and accurate understanding of the universe. So, this is the vision that drives me. Additionally, there are many applications where the lack of accurate physics based models exist. There are no physics based models in many applications within the material science domain. So, machine learning has the ability to step in and address those challenges, and machine learning has already done that as well in many cases. So now let's talk about the type of materials that AI can help us explore and optimize, where AI applications exist. Let's explore some of the types of materials. So there are many kinds of materials. You know it. Alloys, metals, polymers, semiconductors, composites, biomaterials, and energy materials like, those used in solar cells, magnetic systems, and optical technologies. You name it. So each of these applications has unique properties and incredible applications. For example, you already know it, yet alloys are critical for aerospace and automotive industries. Polymers are used in everything from packaging to medical devices. Semiconductors power our electronics. Biomaterials are transforming healthcare, and energy materials hold the key to sustainable future. So the fact of the day is that there has already been tremendous amount of research on each of these materials. Researchers across the world have dedicated their careers to understanding and improving these materials. Industries have poured countless resources into developing the materials. The progress is inspiring, but with AI we can take it to the next level. And by the next level, I will talk about what I mean by the next level in my upcoming talk. So as I say all these things, you all may be wondering, why do we really need AI for in material science? What is the real motivation? Why do we really need it? So this is a very basic question everybody will have by now. So if you go back in history, we can find advanced and critical materials that were totally discovered by accident, and also through Edisonian experimentation approaches, which literally took many years to discover such materials. There are many computational approaches as well, but still they are very slow and may not work when we are dealing with complex material systems. By complex material systems, I mean those materials which contain complex grain boundaries and containing about hundreds of millions of atoms in a unit cell. In such cases, even the advanced physics based approaches also uh, face enormous challenge when modeling, correct? So also there are many applications where the relationships between the structure to property and from process to property is incomprehensible. I mean, there are a lot of applications where the relationships are not comprehensible. And uh, and in such cases physics-based models doesn't even exist. So if you want to discover new materials based on the approaches like experiments, and through this complex physics-based approaches, it can literally take millions of years. It can literally take many years to discover new materials. So we don't want to do that, and particularly we don't want to do that when we are already facing enormous challenges in energy sector, drug discovery, where the discovery process really need to be accelerated. So the question is, so now let's take a scenario where we are trying to explore a design space where there are possibly millions of different compositional and processing parameters. We have different possible candidates in the design space, and now the task is for us to explore that space. Where really machine learning steps in, and we can use machine learning to step through, to search through this space in an efficient manner. Rather than exploring randomly, machine learning can be used to move in the optimal direction, and to reach at the optimal location in a very few steps. So this is definitely one very motivating factor for why we use machine learning in material science. However, like any other technology, machine learning also comes up challenges as well. So one big problem is that uh, the data scarcity. So we know with more data it's like interpolation, but with scarce data it's like extrapolation. And scarce data is the biggest problem, I believe, in materials data. In particular, it has been true in my research. So that when people talk about big data and all the things we can do, and all major companies which do breakthrough research, what they have is very different from what we have in material science. So what the tremendous progress that we are seeing in Silicon Valley is very different from the material industry. Their reality is very different from our reality. They're dealing with data sets of about millions of billions of data points, but the data set that we have is in the range of about 100, 200, 300, 400. There are many cases, but there are many exceptions as well. We do have databases where we have millions of material candidates, but there are many other applications where we don't have a lot of other candidates. So this has been one of the biggest challenge for machine learning, because the recent advancements we see in machine learning uh, has primarily been due to the big data. So another big challenge is that the property prediction is actually intrinsically complex. Like if you are trying to determine properties of these materials, many factors like complex interfacial interactions, heterogeneity, manufacturing defects, and crystal cells, having hundreds of atoms, it makes it all very difficult to model many materials. So modeling the mechanical behavior is further complicated in many other materials that exhibit different properties across different time and spatial scales. I will talk about such materials in my upcoming lectures. So when I say that material behaves differently in different spatial and time scales, probably it might be less comprehensible to the people who are hearing this lecture, but I will talk about them in detail in the next lecture, so you don't have to worry about that. So now when I say all these challenges, one biggest question you all might have is, then how can we use machine learning to discover new materials in a data scarce data context? Right? This is a very difficult question, and that's what many researchers have been trying to tackle. And I will talk about some of the approaches we can use to address the scarce data challenges. I will talk about different materials and how we can use machine learning in a in a scarce data context. Now let's look at the key elements in machine learning, specifically for material science applications, and it's also true for other applications as well. So these elements form the foundation of the machine learning pipeline, and are also applicable to other fields as well, right? The first thing is, of course, we have to define the problem. First, we have to define what the problem is exactly, and that takes a lot of time in a lot of research areas. Understanding the problem we are trying to solve is the cornerstone of any AI project, and this steps sets the direction for everything else that we do. Next step we usually do is collecting data, determining and collecting the data takes usually a lot of time, which probably people don't appreciate so much in many cases, but it does take a lot of time and energy and effort. And the next step is determining the input features and their representation. So in material science, this could involve the data collection could involve experimental data collection, simulation results, or data sets from literature, and deciding how to represent material properties in a way that the AI model can understand. So, these three steps, problem definition, data collection, and feature representation, are deeply interconnected. So, and I will be dedicating a few videos to explore them in detail. And I will be talking, because they're interconnected, I will be talking about uh, them in tandem, so that I can connect these few steps, because it's necessary to connect them. And after that, I will move on to uh, the more technical aspects, like AI model, the loss function, and optimization. You know, here we'll discuss how to select or design models suited for material science, how to define loss functions to guide learning, and how to optimize the model for the best results. So these topics are vast, and I will cover them across many videos to ensure each concept is thoroughly explained, and I will talk about them from scratch. But having said that, I will not go into details into the traditional ML models in details, because those resources are already available in YouTube, and I will share their links in the YouTube description. So, by breaking down this way, I hope to provide a very clear and structured approach to understanding machine learning for material science and other domains. So, let's dive in each of these things, like defining the problem, collecting data, input features, representation, AI model, loss function optimization. In the upcoming videos, we will see in the next videos what they are. Until then, don't forget to subscribe and like it, so that I can create more videos like this.